All right. So I wanted to give a bit of context for this workshop. So I'm a theoretical physicist by training, and essentially have been working in statistical physics when I was doing my PhD work, and what people call machine learning or statistics certainly has classical relationships with statistical physics. And I've just noticed that there are these new opportunities for, I would say, theoretical physicists, field theorists, statistical physicists to engage in questions that are now of practical value. And it seems that this knowledge has not spread widely in the physics community. And I think India has a strong theoretical physics community. Once this knowledge becomes more widespread, I think there would be a lot of research opportunities. These are really opportunities to do theoretical work. In fact, I've gone to ICML now twice, and twice I've seen talks on, using random matrix theory, not necessarily terribly, profound applications, but definitely things that are, I think, of interest to the engineers. And so this workshop really is to stimulate the connection between the computer scientists, people who are working in machine learning, and theoretical physicists who might want to join into understanding some of the phenomena that are being empirically discovered in an engineering mode. My talk will not be about deep learning. I'm going to talk about some work that I've been doing, but it may relate to optimization as is done in some of the modern machine learning. But I will give a little bit of kind of, I think, conceptual or just ideas context. And my talk will be mathematically relatively elementary. So I would say that what you should be looking for here are more the ideas than the math. I do want to begin by pointing to what I think is the first deep network. Nobody cites this, but a Ukrainian control theorist by the name of Ivaknienko. I think he did this work in the mid-60s. 4 layers, actually quadratic nonlinearities. Just to show that even though this field is extremely popular, there is an old and relatively large and some of it uncited literature, fairly diffuse out there. So as you could see from Rina's talk, there is essentially like a zoo of deep network architectures. Why they are called deep, by the way. I think multi-layer perceptrons is how I would think of them. But they do remain kind of ad hoc and fairly handcrafted. So Google's answer to this seems to be AutoML, that is learning the network architectures themselves, although I read some blog posts somewhat unkindly suggesting that this is just a hyperparameter learning called AutoML. But then there was, some New York Times article about this. But I put that up just to say that, of course, biology already has AutoML. It's called evolution. And in some sense, brain circuits are, and I don't want to say this in a technical mathematical sense because I don't think it is correct, but one can maybe in some heuristic way think of brain circuits as kind of nature's algorithms, solves problems. And what I've been interested in is I've got like 2 components to my own research. One is to study brain circuits, so it's in some sense study nature's algorithms, and I'm doing this experimentally. I started out as a theorist, but I have an experimental research program as well, and I'm mapping brain circuits in the mouse and in the marmoset. So not going to talk about this, but ask me if you're interested. It's very interesting data, and lots of opportunities for machine learning to just to analyze the data, because these are petabyte scaled data sets. But independently, I have also been studying distributed algorithms, essentially trying to apply those things that I learned in theoretical physics to problems in control theory and machine learning, where there are many variables involved. And what I'd like to do is to really compare the two and ask whether there are the same underlying principles and patterns that recur in these wet and dry circuits. If they do, then those would be, if you want, the laws of intelligence. So if one can find those, then we'd be very happy. And I have particularly focused on the whole brain rather than individual, rather than sort of micro circuitry. But I'm not going to really talk about any of this. I mentioned this just so that you know I work on it and you can talk to me about it. But I want to return to this theme that, in some sense, physics strikes back. And what's interesting, I had a control theorist friend, I have a control theorist friend at UCSB, and he said he was looking at recent hires or talks in the computer science department, and they were all essentially doing numerical linear algebra. So things, the sorts of things that physicists have done traditionally, not really, let's say language theory or computational complexity or things like that. So physics or continuum math has been taking revenge on discrete math. And this is why I think physicists should enter. I think my battery has died on this thing. All right, so objects are being represented as points in vector spaces or Hilbert spaces. And even a sentence, people are thinking of as a random walk in a high-dimensional vector space. So very different from thinking of a discrete kind of sequence of symbols, which is the traditional kind of computer science way of thinking about at least modeling human language. Another idea from physics, which has been influential, although even physicists don't realize this is an idea in physics, which is linearization by lifting to high-dimensional spaces. So early days of quantum mechanics, there was something called Koopman linearization, which essentially took nonlinear ODEs and made them into linear PDEs, just for even in classical mechanics. And so converting problems with nonlinear decision boundaries to problems with linear decision boundaries in high-dimensional spaces has been a theme in machine learning. Certainly group theory physicists love symmetries, and you just learned about how influential simply the observation of translational invariance has been in these image processing applications. And perhaps the most intriguing thing is what I call thermodynamics of big data, which is that physicists essentially have been doing probability theory with many degrees of freedom. And that's also relevant for modern machine learning. So in many ways, there is room for a dialogue between physics and computer science that can be, I think, very productive. And I think the hope is that this workshop will stimulate some conversations between computer scientists who are here and physicists who are here, and lead to a productive research program. So I've taken this example, a slide from Sanjeev Arora's work. And I don't know how many of you have seen this before, but as I said before, just to illustrate that words are being represented as vectors, word analogies can be, in some sense, looked at as, so there's a word vector for man, a word vector for woman, and then a word vector for king, and one looks for what is the closest word vector by solving this minimization problem, and then one finds that that correctly predicts that one should get, king as to queen. this is the point about linearization that I made a minute ago. I won't go into this in detail. The idea of group theory being useful. So Stefan Mallet has done some work, which is very nice, where he uses also just scale as well. And then instead of learning the weights in a deep network, he makes a feed-forward network where all the weights are fixed. They're essentially cascaded, windowed Fourier transforms, wavelet transforms. And then at the end of it, he just puts a shallow network or just a linear regression, which is where you do all the learning. And it turns out that this particular network, where if you, in some sense, the weights are chosen in a principled way, thinking about symmetry, has quite good performance on the MNIST data set. So what I'm going to talk about today a little bit more is this issue of thermodynamics of big data. And I think this is a general phenomenon beyond machine learning, that modern engineering systems have large numbers of degrees of freedom and require probabilistic tools for analysis. Physicists have developed calculation methods for treating high-dimensional probability distributions in the context of statistical thermodynamics, quantum field theory, and so on. And one can bring those tools and analyze the properties of machine learning algorithms, distributed control algorithms, assuming that the parameter sets are random, that they are chosen from some suitable high-dimensional probability distribution. Now, of course, they are not actually random in a given engineering context. You have a power grid. The topology is may not be regular, but it's chosen for a very specific reason, perhaps engineered. But you can pretend as if it was random when analyzing it. Similarly, in the machine learning examples, this sort of randomness assumption allows analysis of the optimization algorithms. This approach is, of course, familiar in physics. For example, we don't know, let us say we don't want to deal with all the complexities of the Hamiltonian that we would need to do if we wanted to do ab initio calculation of nuclear energy levels. Actually, I don't even know what the current status of that is. Perhaps Spenta will make a comment on it. But one can just assume that it was a random Hamiltonian, and that leads to certain predictions, like the spacing between the energy levels can be predicted, just assuming that it was random. So this theme is, of course, there in physics, and in fact, there in statistics as well. The study of random covariance matrices, the so-called Wishart distribution, in fact, predates the application of random matrix theory to nuclear energy levels. So this idea has been kind of going back and forth. So one thing I've been interested in is, in the thermodynamic limit of having many variables, there are things which one might call performance phase transitions. And what that means is you go from a regime, when you vary a parameter, to your system working perfectly well to failing completely with no kind of intermediate gray zone. And this kind of interests me because of this somewhat abstract question. Brains are distributed noisy networks. And the question is, under what conditions do distributed noisy networks perform tasks reliably and accurately? I'm going to talk to you about two specific examples here. One, the so-called network consensus problem, which you can think of as distributed addition, and the other one is feature selection, which some of you are familiar with in the context of lasso or elastic net algorithms. In both of these cases, there will be performance phase transitions. And I want to point out that we are living in this era, at least in biology, of parts lists, where people are making kind of typology of neurons in the brain or even cells in the human body. So there is certainly an enterprise which is well-funded, and there's a lot of community effort going into it, categorizing all the different types of neurons in the brain, all the different types of cells in the body. And the question in my mind is, well, once you have that long parts list, have you actually understood how the brain works? Because it's really a circuit that gives the brain its properties. And looking at individual elements in a disconnected way may or may not tell us how that connected circuit works. Now, this is, of course, a very well-known theme in physics. I've made up this kind of analogy to illustrate maybe a connection with biology. So we recently had Hurricane Irma, which was caused a lot of damage. The peak speeds of Hurricane Irma, that's 200 miles per hour, is 90 meters per second. And so if you look at the root mean squared velocity of air at the same temperature, that's 500 meters per second. So Hurricane Irma, if you look very closely, in fact, looks like this. It looks kind of random. And on the right-hand side, I have put down some single unit firings from, this is just not from this particular tiger's brain, but if you stick electrodes into the brain of some animal, you're going to see something like this, noisy looking thing, sort of resembling what Hurricane Irma looks like at a very microscopic scale. But of course, at a macroscopic scale, here's your tiger jumping to eat the bird. It doesn't look so random. It looks much more deterministic. So I would suggest that while the two are mathematically connected, looking at the microscopic detail, if you don't know how to read the microscopic detail, can really mislead you about understanding the macroscopic phenomena. And I think that this is a problem that biology suffers from, in the sense that there is a lot of detail in biology. One, of course, doesn't want to become this kind of unreconstructed holism where we are in a mystical state about emergent phenomena. But one certainly has to think about the connections between what is happening microscopically and what we are observing macroscopically. Physicists have thought about that a lot in the context of physical systems, and maybe some of that mathematics carries over. It has not been the case in the past that has happened. It has been tried, that research program has been tried, but maybe this is a different angle. Let's look at engineering. So let's leave aside biology for the moment. In engineering, we kind of have better control. We have all these degrees of freedom, and it could be machine learning, could be robotics, could be distributed power grids. And let's try to connect the microscopic and the macroscopic, and look at maybe phase transition phenomena, collective phenomena. So qualitatively new phenomena appear in the large N limit, not a surprise to physicists in the audience. Phase diagram of water, but think of it as a network. Network being the water molecules interacting with each other. Interaction rules make them a network in some sense. It's the same network, but you change one or two parameters: the average kinetic energy, the average pressure, and then you get dramatic changes in the behavior. So the idea is that similar things can happen in engineering phenomena and in biological phenomena, perhaps. I'm saying thermodynamic, but this is not hypothetical. Rina was talking about millions of variables. So the number of variables, we are essentially talking about 100 million parameter fit, billion parameter fit. The number of parameters are becoming astronomically large. In 2016, I understand that IP traffic was measured in so-called zettabytes, and we are running out of kind of acronyms here. I would like to suggest a different way of measuring things for these very large numbers. So 1 zettabyte turns out to be 1.6 milliavogadros. So we can start thinking in terms of Avogadro number. Okay, maybe not quite Avogadro number, but things are reaching kind of macroscopic proportions. So phase transitions have played a very important role in the history of statistical physics. This is due to the non-analytic behavior of the free energy in the large n limit, starting with the Ising model to understand ferromagnetism, Landau's mean field theory, then exact solutions of the Ising model, renormalization group theory, and then the understanding of disordered systems. So this history is well known. Perhaps what's not so well appreciated is there's a parallel history in engineering, a little bit delayed from the physics history, which also has kind of phase transition phenomena appearing in different engineering domains. It's a consequence of having lots of variables. I'd say that the error correcting codes of Shannon is perhaps one of the first and very elegant examples of such phase transition behavior. But there are other ones. Computational phase transitions in the typical case, which I think perhaps we'll hear more of from Yoshiyuki in his tutorial, where there has been this easy, hard, easy phase transition, where with change in a certain parameter, the problem goes from being tractable to being intractable and then being tractable again. And phase transition examples have appeared in machine learning already, in communication networks, and somewhat more recently in distributed control theory. So I was doing some work on this when I was at Bell Labs in the context of communication networks, and there the so I won't go into the details of this, but more recently, sort of re-engaged in this, and this will be the first case study that I will tell you about, which is the so-called consensus problem. You can also think of it as distributed addition or the car platoon problem. So we live in the era of self-driving cars. That's coming soon. So once you have one self-driving car, you'll have many self-driving cars. And once you start having many self-driving cars, then interesting collective phenomena may appear. So one question that was asked to me by a engineer friend, Bassam Bamieh, several years back, he was describing to me how there were these platoons of cars on the highway, and the idea was that the cars would maintain a certain distance. By measuring the distance from the next car, they would try to maintain that distance. And I immediately pointed out that, well, in physics, we know that you cannot have long-range order in one dimension from short-range interaction, so I would expect that this won't work if you have a sufficiently long formation of cars. And of course, he didn't believe me, which was very surprising, which taught me that facts which are elementary in one field may be non-trivial in another field, which is a great way to, kind of make research progress. That's perhaps the subtext of this of this workshop. So then we set out to, in fact, investigate whether, after one has looked at the details of the control theoretic algorithms, the physics intuition still holds, and the answer is yes, it does. Still hold, not terribly surprising. And there's this paper which the control theorists liked, which said that just due to the graph topology, there are fundamental limitations to distributed control that very similar to what happens, the reasons why order cannot happen in lower dimensional systems in physics. So here's kind of a simplified problem statement. And this is the simplest distributed computation you can think of, which is just addition. It's just adding numbers together. And no, if I will give you a little more precise, if there is noise, and if your control law is local, then in the limit of long formations of cars, no, it is not possible to, it is possible to maintain the distance between cars locally, but it's not possible to maintain the distance between the first car and the last car in your formation. So here's a simple problem, and this problem is almost, it's quite trivial in some way, but I think it's a useful thought exercise. So if I gave you n numbers and you wanted to compute their means in a central way, you just take a register and you keep adding those numbers together. But supposing xi are living on the nodes of a graph which are not fully connected, and only nodes connected by edges are allowed to communicate during the computation. So that's the rule of the game. So the network consensus problem says xi live on the nodes of a graph. They can drift due to additive noise. So think of clocks on a network, and these clocks need to be synchronized. This is an important problem. If you don't have way of instantly communicating across the network, which we don't, propagation speeds are always finite, and we want to know when something happened, we want to share the notion of time, then we have to synchronize clocks. So think of xi as the clock phase at node I, and each clock is drifting with some little jitter. And the question is, can I, just by looking at my neighboring clocks, come up with a feedback law that will keep my jitter well controlled? So I've written that out. So this is just a local control law. And the objective is that the variance across nodes remains small. So the variance is just xi of t minus the mean over all the nodes at any given time. And I would like this variance to remain small over time. Now note that if there is no control at all, if kij's are 0, then of course xi's of t just do a random walk, and so the variance will grow linearly. So if you started out with a bunch of clocks, then they would all drift. The intuitive idea is that one can update with an average over the neighboring sites. So this is the simplest kind of algorithm one can think of, and this is called the network consensus algorithm. And physicists will instantly recognize diffusion. And so this is kind of diffusion with a little bit of additive noise. The control law is just a graph Laplacian. And lest you think that this problem is too simple, I just want to point out that I just went to NIPS and I found out that somebody was doing essentially consensus algorithm to do parallel stochastic gradient descent. You distributed your computation across nodes, and somebody noticed that, well, having your the parameter server centralized causes a lot of communication costs, so they created a ring topology to communicate only between neighbors on the ring. Of course, from our work, you would see that the ring topology is the worst possible topology you could choose if you had, if you were to lay out the network, for a big ring. And in fact, you can recognize the consensus algorithm right here. So what's being computed here is not the network mean, but you still get kind of the graph Laplacian entering in. So relationship between network consensus and distributed addition is as follows. The consensus dynamics leaves the network mean unchanged. X bar of t is going to be x bar of 0. So if we can somehow arrange that sigma squared of t remains small or even shrinks, then each network node will end up approximating the network mean over time. So consider the d equal to 1 case, which is just nearest neighbors on a line. And so that's just one-dimensional discrete diffusion. So what happens to the variance as a function of t and n? So you could either let t remain fixed and let n go to infinity. What you find is, unfortunately, the variance still grows, not linearly with time, because you've got some control locally, but it grows like the square root of time. And on the other hand, you could let t go to infinity, and you could look at the variance as a function of network size, and that grows linearly with the network size. And that you can see pictorially here. So in blue, let us say, you started out with this random jitter in the clocks. So this is positioned along the 1D chain. And one applied a little bit of diffusion. That's what happens after 10 time steps, the red curve. So it reduces some of the variance, but then you wait long enough, the long wavelength modes are not well controlled in one dimension, so they build up, and you start getting these sort of long wavelength fluctuations. And of course, you can do all of this analytically. I just show it numerically so that you have a mental picture. And what happens to the variance as a function of time for d equal to 1 consensus is that first the variance drops, then it starts going up. And it actually should go as the square root of time, but you can't really tell from this numerical simulation, which was not meant to pull out the power law. In higher dimensions, the variance will depend on the spectral dimension of the graph. This graph could be a fractal, so the spectral dimension could be non-integer. The spectral dimension is just defined by the return to the origin probability of the random walk being given by 1 over time to the d over 2. And so here's what you get in higher dimensions, which is that the variance grows like t to the 1 minus d over 2. So that's why it grows like square root of time in d equal to 1. And it's fairly straightforward to understand why. So we can go to a continuum version of the consensus problem, and that's just diffusion with some additive noise. And there are two pieces to this. One is if you look at the value, so x is now the variable, spatial variable, and phi is the value, like the clock phase. The initial values get smoothed out by a Gaussian, but then there is additive noise, which also builds up, smoothed by a Gaussian. And pictorially, what you see is, well, you started out with some initial fluctuations, those get smoothed out, and those fluctuations will eventually go away with time. So if there was no additive noise, then the network consensus, then the consensus algorithm would compute the distributed mean at sufficiently long times, not very surprisingly. I've assumed uncorrelated spatial fluctuations here. But the second term, if you calculate that one, then what you find is that it has an additional power of time because you have to integrate over the noise that's building up at each site. So the noise variance is the noise variance generated per site, and then the number of sites averaged over, which grows like the diffusion volume. So that's why you get t to the 1 minus d over 2. So similar phenomena for the formation of self-driving cars. It's second-order dynamics, but doesn't really make that much of a difference. And so this is what happens in the highway then with the self-driving cars. The first and the last car start having very long fluctuations between them, which wouldn't be very good. If you, the variance grows linearly as the number of cars. Yeah, if you write it will stabilize to a variance that's linear in the number of cars. Excuse me. And the square root with time. Sorry, that was just, this is time, and this is just the position of so each individual wiggle is the trajectory of one car. So the height is like the distance between the first car and the last car. So mathematically, this result is trivial in a sense, but it's just a consequence of the spectrum of the Laplacian. But you can also put in different types of feedback, and based on whether there is absolute velocity. So one way you can control it is knowing an absolute position and absolute velocity. And you might think that you have a speedometer and you've got GPS, so you should be able to get absolute position and absolute velocity, but there is noise in those measurements, so you have to really account for these things. So I'm not going to go into the details here, but one phenomenon familiar with physics appears here, which is the dimensionality of the graph is very important. So in the power grid or in these self-driving cars, the dimension is not going to be a cubic lattice of some sort, but there may be some effective dimensionality. And again, the systems may not be infinitely large, but it's going to have some effective dimension. And it's a useful way of thinking about this. And as I showed you, in these parallel distributed stochastic gradient calculations, there's also some network topology of computers over which the computation is taking place. You can ask whether memory would help. That is, if I integrated, I put an integral control. And the answer is that, strictly speaking, no. So if you have, this is the static feedback case. If you have dynamic feedback with noise, the variance still grows with the size of the system, but it is actually reduced. The slope is reduced, which is nice. If you have dynamic feedback with no noise at all, then what you can do is you can integrate and you can figure out where exactly you were. So you end up with absolute position feedback. And then, of course, you can go back to the case where you can maintain your formation. So there is, in fact, some theorem that says that no linear local feedback control law will give a better asymptotic performance than just a simple Laplacian-based control law. Thus, purely topological considerations on the graph produces performance limitations, and the transition takes place with respect to the graph dimension, in this case. Now, here's a problem, which is prove that this is also the case for nonlinear local feedback control laws. One believes that having nonlinearity shouldn't change this picture, but that theorem hasn't yet been proven, so open problem for somebody to prove. How about multiplicative noise? So it could be that the nodes are communicating, but there is some fluctuations in the communication link between the nodes, and that we could model as multiplicative noise. And this is work that's done also with colleague Clément Cyr. And what happens there is that you end up with a phase transition as a function of the noise strength. So if there is small amounts of multiplication noise, and in the case of exact conservation, so that the multiplicative noise doesn't change the conservation properties of the dynamic, so it preserves the local mean. In this case, for small enough noise strength, you see the behavior. So this is dimension, this is noise strength, and in this regime, to the left-hand side of the red curve, one observes the behavior that I just told you before, which is that above 2 dimensions, one can get a finite variance. Below 2 dimensions, one gets a variance that grows with time. But above this curve, one in fact gets exponentially growing variance. So that says that for a certain amount of multiplicative noise, in fact, the system becomes exponentially unstable. If you don't have the local, so it's instructive to look at above 2 dimensions. If one looks at the noise variance, it has a limit as n goes to infinity. And the additive noise variance is kind of, in some sense, renormalized by this 1 minus the strength of the multiplicative noise variance, and this thing can diverge. And that's why one gets this sort of transition with the multiplicative noise. And multiplicative noise is fairly ubiquitous. If you have additive noise plus nonlinearity, that will convert things into multiplicative noise. So let's say there is some distributed algorithm, and it is performing, to a certain extent. There may be a certain amount of noise, maybe rounding error, at which the algorithm will catastrophically fail. So that would be the way to think about this. Now, it gets worse if you don't have this kind of local conservation, and if you have only average conservation. It turns out that the exponential behavior sets in even for 0 noise threshold when you have your graph is less than 2 dimensions. Excuse me. That basically says that there is no robustly stable local algorithm in D less than 2 for distributed addition, when the performance criterion is the variance or the second moment. So this is the simplest possible calculation one can do in a distributed way, just adding things up. And you can see that in the limit of large system sizes, you can't even add things up because noise will kill you. And it'll kill you because of the multiplicative noise problem. And that's not entirely intuitive. I think that at least in the engineering literature, when this sort of problem is studied, usually it is studied for small system sizes or maybe for certain kinds of graph topology. So I'm actually interested in studying this behavior perhaps with the distributed optimization problems that people are now performing on these multi-million variable problems on bunches of computer GPU nodes. And there, the interest may not be so much in noticing there's a phase transition, but in designing the network so that it does not have a phase transition. You want to be in the good phase, but in order to be in the good phase, you kind of want to analyze. And unlike this simple problem which I have analyzed, which is everything's linear, once you throw in nonlinearities, things will become a little harder to analyze. But probably the same behavior survives. So more complicated distributed algorithms should be studied. The second case study is one that has been fairly well studied before, including by members of the audience, but I will go through it for those of you who are not familiar with it. And this is feature selection in multivariate regression, phase transitions in lasso and elastic net algorithms. How many of you are familiar with the lasso algorithm in this audience? At least half of you. Let's say I give you M measurements, 100 measurements, but you have many more unknowns than you have measurements. You've got 1,000 unknowns. And this may seem, why would you ever do anything like that? But you can imagine you're doing a clinical trial and there's only 100 subjects in the trial, but there are many, many, many variables which could potentially affect the outcome of the trial, and you don't really want to rule out those variables a priori. We will have to impose some constraint, of course. Without imposing some constraints, we cannot have more unknowns than measurements and do anything. So here's a simple setting of the problem. M measurements, n unknowns in this parameter vector x, but the matrix H that connects the measurements to the unknowns is known. So this is the so-called design matrix. And traditionally, one would minimize the least squared error. So one would say, let's find an x or some family of x's that minimizes y minus hx squared, and this would lead to the pseudo-inverse if one looked for the minimum norm solution of x. Now, what has been done typically is to traditionally, what has been done is to use a thresholding procedure, a greedy procedure, to keep only those parameters. So you do your data fit and you find some parameters and you say, well, all these parameter values turned out to be very small, so I'm not going to keep them. I'm going to set them to 0. You apply some statistical test and you threshold it by computing, let's say, an F ratio. So starting in the 90s, there is a statistical procedure that has become very popular. I think first by Tipshirani, which is to say that let us minimize y minus hx squared, but with a penalty that's not the square of x, but the sum of the absolute values of x. And this is a convex relaxation of a non-convex hard problem where you might say, well, I just want some of the x values to be non-zero. I don't know in advance which ones. So let's say out of those 1,000 unknowns, I only had 10 non-zero values, but I don't know which 10 out of the 1,000. So I would have to do 1,000 choose 10 different combinations. I have to try all of those. So that would be computationally expensive. So instead, if you minimize this problem, this can be solved in polynomial time. using linear programming. And what Donahoe et al. Showed is that this problem has a performance phase transition between good and bad phases. Now, there is some historical background to this that is not often pointed out. When I was at Bell Labs, in fact, I was told about L1 minimization for sparse frequency estimation by Logan, who was in his PhD thesis. And in some sense, you can look at Prony's method for recovering multiple sinusoids from data as being related, and that dates back to the French Revolution. So, people have been doing variable selection using something like an L1 penalty before. So here is what the phase transitions look like. So here is successful reconstruction. So this is some simulation. Won't go into the details of the simulation. It's from this book, which I really like. I'd recommend as a reference book. So if you don't have enough measurements, then you cannot reconstruct. So there's a sparsity constraint. So there's 1,000 unknowns, and only 20 of those 1,000 unknowns are going to be non-zero. So as you increase the number of measurements, you go from not being able to recover to being able to exactly recover with this S-shaped curve. And as you let the number of unknowns or the number of measurements go to infinity, keeping ratios fixed, then this S-shaped curves, in fact, becomes a step function. And that's your phase transition. So these are two different algorithms. So that's basis pursuit, the one that I just told you about. But then there's another algorithm called the hard thresholding pursuit. And it gives a different boundary. And in fact, basis pursuit is not necessarily the best for every possible combination of the problem setup. Here is a situation where, in fact, hard thresholding pursuit is doing better. This is numerical work. So as a physicist, I guess one can ask, what are the universality classes of algorithms? What are their phase transition boundaries? How do you compute them? And some of that work has already been done, but just to give you an indication of the sort of opportunity that exists here. So here's the phase transition curve laid out for you. This has been derived many times with many different methods, but it's very useful, I think, to keep this one in mind. So uncorrelated Gaussian H. So H is known, but it's picked from a Gaussian random ensemble with uncorrelated entries. Y is an m-dimensional measurement vector. H is m by n, and x is n-dimensional. Two parameters. Alpha is m over n. One can think of it as the undersampling parameter. So m is less than n, you're undersampled. Larger alpha means more measurements. Rho is a sparsity parameter. Rho is k over n, and k is the number of non-zero parameters. Again, you don't know which particular parameters are non-zero in advance, but you know that k of them are non-zero. So rho is k over n. If rho is sparse, if rho is small, then you have more sparsity. If rho is large, you have less sparsity. When rho is equal to alpha, the number of measurements is equal to the number of non-zero unknowns. So you can imagine that unless the matrix H was badly behaved, had a low rank in some way, that you'd be able to invert this problem, certainly using the combinatorial method, and if there was no additive noise. And so this diagonal line is above which you can, in principle, recover, but using combinatorial algorithm, which is not going to be practically feasible for any large sample size. In this regime, recovery is not possible. So it's a bad regime. So this regime is also kind of bad because of computational reasons. And this is a good regime where that L1 algorithm will provably recover. And this red line has this analytical form is the phase transition boundary. There are several approaches. As I said, both Yoshiyuki and Surya have worked on this problem using replica mean field theory. The original approaches were using combinatorial geometry. The work that I've done in collaboration with Anirvan Sengupta and his graduate student used the cavity mean field theory. Just going to point to a couple of the results. You can look at the papers. For these two algorithms, Lasso has the penalty term, which is just the absolute value, just the sum of the absolute values, and Elastic Net has an additional quadratic term. Physicists recognize different universality classes by looking at critical exponents. And what's interesting is that non-trivial exponents appear even in this problem. Now, this is mean field exponents, and these are infinite dimensional models. There's no space, which is why these exponents can be exactly calculated. So if you look at the mean squared error in the basis pursuit case, and you look on the phase transition line itself for finite values of lambda, then you find out that the mean squared error goes lambda to the 4/3, and for elastic net, it goes as lambda. So basis pursuit actually is behaving better, because for small values of lambda, lambda to the 4/3 is smaller than lambda. So it's outperforming the elastic net. This is only for uncorrelated entries. That's not necessarily going to remain the case for correlated entries, because the phase transition curves themselves will shift. But the point is that there are different universality classes of algorithms to consider. I mean, we haven't really finished exploring this problem. This is meant more as a teaser for people in the audience who thought they were done with exponents. But maybe there's more fun to be had. But it's not just exponents. You can calculate the quantities of interest. Like here, the mean squared error is being calculated as a function of the alpha parameter, so the solid lines are the analytical calculations, and the dotted, those are just the symbols. And there's a zoo of exponents. Depending on what the non-zero values, how they're distributed near the origin. Now, here's something that's also of practical interest in using this kind of method, which is what value of lambda should one choose for a particular case. We were able to calculate these. So the mean squared error versus lambda, and it has a dip, so it sort of tells you what value of lambda to choose. And I should point out that all of these are, the minimum for small values of everything is lambda goes as noise variance to the 2/3 power. If H has correlated entries, then the phase transition boundary changes, and this is the part that we did. So I had done some work previously with Anirvan with correlated matrices with correlated entries in computing distributions of singular values. So actually, let me just go here and say that, so the red line is the uncorrelated case, and then these symbols correspond to simulations done with the correlated entries, and the phase transition boundary shifts upwards. It makes sense if the entries are correlated, you need more measurements. So that's sort of the physical meaning of the shift of that phase transition curve. And then these two problems that I've shown you, the consensus problem and the lasso problem, can be combined. So in more recent work, which has not yet been, so another problem, people who want to calculate phase boundaries, this is available in preprint form, but it's a distributed hard thresholding pursuit here, some version of hard thresholding pursuit, but in a distributed manner, where the matrix is not available centrally. So some rows of the matrix can be very large. Let's say it's an m by n matrix. M is 10,000, and n is 1,000. Then the matrix is 10 million, so you don't want to share the, or choose larger numbers. So the matrix is only available partly at each node. There is the vector x, which is unknown, is supposed to be the same for each node, and each node has its own set of measurements. And so a distributed iterative algorithm that mimics the consensus problem, which you can see here, or in physics terms, there is a Laplacian in there, if you were to think of the equilibrium version of this. And again, there are these sharp cutoffs in recovery. So I'm going to close there. And my specific conclusions are that there are dimension-dependent limitations of distributed control in the large N limit. One can analytically derive formulae for phase transition boundaries for the consensus problem with multiplicative noise. And distributed addition is not robustly possible in D less than 2. I've showed you that one can calculate analytical formulae for a variety of objects of interest for elastic net and lasso, and including for some correlated measurement matrices. One cannot do it in general. The correlated case is much harder. But what's interesting is perhaps there are different universality classes. And there is a phase transition in the distributed hard thresholding pursuit problem, which would be interesting to compute. Broader conclusions are that network sizes of distributed computational control in real-life applications have reached thermodynamic proportions. So certainly the biological brain has many neurons, and we are mapping the circuits, even if you look at particular subsystems. That may be less tractable to study in some sense because you don't really know what's inside the brain. We are still mapping it. But again, for these large engineering systems, which we control well, I think it's really a very promising, I would say, area for graduate students entering the field who would like to connect with real applications, and at the same time, there may be some theoretical problems that the physicists themselves have not studied. The question in my mind is, do nervous systems take advantage of these large N phenomena beyond simple redundancy and averaging? Do they have interesting architectures where they are taking advantage of performance phase transitions? And my suspicion is that they do. It'll be difficult to prove something like that, but it's an interesting hypothesis. And perhaps you can explore that question more in an engineering setting. And I think that just bringing in sort of ideas of scaling and phase transitions into brains haven't really worked out so far. People have tried that a lot. So that's why I'm taking this more kind of measured approach, but one certainly has this idea in mind that there's a reason why we have so many neurons and we are doing this very distributed noisy computation, but we seem to be doing fairly well. We don't, we are able to perform reliably and accurately at the end of the day. I'd like to acknowledge my support, and we'll stop there. I guess take one or two questions, but also room for discussions later. Yeah, effectively, these are computations of the variance, so they are Green's function computations for the linear problem. Yeah. For the nonlinear problem, one would probably compute some correlators and still hope to find similar behavior.
If you considered the vanilla averaging scheme for computing the average, there's another linear iteration to compute average, which will be more stable, so it can handle noise also. A little more complicated.
Which is what?
Based on the Poisson equation, what we call Poisson equation. I can tell you afterwards.
Okay. Well, the point is that any local scheme won't work. All local schemes will have the same behavior. Because any local scheme will suffer from the same limitations that.
You see, the averaging you do, it's a marginally stable linear system. So it has one eigenvalue on the boundary of stability. That's why the noise doesn't get killed. But the other scheme, which I can tell you later, is completely stable, so it doesn't have this problem.
Well, there's a theorem that says that you cannot stabilize a platoon of cars.
There must be
control.
some. Maybe the scheme doesn't fit the whatever.
Maybe there's some non-locality.
Likely it's more involved. I mean, it's not
you'll have to look
so
at
transparent.
It. But there is a theorem in there, so it's not a loose statement. Break for lunch.